In this video we're going to consider how we can apply our understanding of calculus to straight line motion, and this is something that we're already pretty familiar with, the idea that we can differentiate and integrate to move between the concepts of displacement and velocity and acceleration and so on. So we could be talking about straight line motion in a horizontal direction or a vertical direction, and they're typically the two ways that we'd think about it. So something could be accelerating. Its velocity could be changing as it moves backwards and forwards or up and down. And so I think we'll get straight into an example. And this one's not particularly difficult from the maths, but good to try and highlight some of the conceptual sort of stuff. So here we go from exercise 14a. The first question talks about the position of a particle travelling in a horizontal line relative to a point O on the line is x meters at time t seconds, and its position can be described by this equation for t greater than or equal 0. So that's a pretty typical sort of setup for a question like this. In this case, we're given an expression for position, which is really another way of saying displacement, isn't it? So if we thought about our straight line here, we've got some fixed point O on the line, and we might say, well, let's let that direction there be positive, which I guess is pretty typical given the number line, and the other direction's negative. And so for times greater than or equal to 0, this equation here is describing where this particle might be. So if you look down at the things that we're being asked to find here, we've got displacement, we've got average velocity. It talks about the relation between velocity and time. We're trying to find a velocity at a specific time, when and where the particle changes direction, the distance travelled in the first 4 seconds, and the particle's average speed. So we do have average speed and average velocity. We also have distance and displacement. Conceptually, then, we need to make sure that we're clear on the differences between those. So let's write down here our equation. What is it? 1 plus 2t minus t squared, valid for times greater than or equal 0. First of all, we're trying to find the displacement of the particle in the 3rd second. It's a slightly strange way of saying it, maybe after 3 seconds. So we're just wanting to sub in there, aren't we? So it's that 1 plus 2 times 3 minus 3 squared. That's me 1 plus 6 is 7 minus 9, so that would be negative 2, and we know that x is in meters, so negative 2 meters. So we're clear on the fact that that just means 2 meters to the left of that reference point O. Alright, the average velocity in the first 4 seconds. Well, we know that average velocity or average speed is going to be related to distance divided by time, but because here it's average velocity, it's going to be the displacement divided by time, isn't it? So if we were going to write a little expression here, we could say average, I shouldn't say average displacement, I should say average velocity will be equal to displacement divided by time, and we're doing it for the first 4 seconds, so x4 minus x0 over the time, which is 4 seconds. So if we sub 4 into here, what have we got? 1 plus 2 times 4 minus 4 squared, and subbing 0 into that just leaves us with 1. That's all divided by 4. So what's that? The 1's are going to cancel. We're going to have 8 minus 16, which is going to be negative 8 over 4, which is going to be negative 2. And our units here are meters per second. So do we appreciate that what that's saying is that on average, during the first 4 seconds, the rate at which the position is changing is 2 meters to the left per second. 2 meters per second in this direction. Now that doesn't mean it's always traveling this way, and it certainly doesn't mean that its speed is always 2 meters per second. but on average for those first 4 seconds. So part of the time might travel this way, part of the time might travel this way, but that's on average in those first 4 seconds the way that the position or the displacement is changing. Alright, let's get rid of this up here so we can, let me change that there. Let's get rid of that so that we can write up here. Now we're up to part C, and in part C we're trying to find the relation between velocity v and time. Well, that's just a way of saying what is an expression for velocity, and we know that we can use calculus there, so differentiating that, we've got derivative of 1 is 0, derivative of 2t is 2, and derivative of t squared is 2t. And that would be, if we wanted to write some units, would be meters per second there as well. Alright, that's all that part C is asking. Part D, find the velocity of the particle when t equals 3. So velocity at time 3, 2 minus 2 times 3 is negative 4 meters per second. What about the next part, E? Find when and where the particle changes direction. Okay, massively important conceptual understanding here is that an object moving in a straight line changes direction, or in order for it to change direction, its velocity must be 0. So to find changes of direction in straight line motion, we let the velocity equal 0, because if something's traveling this way and then it changes direction, it has to stop momentarily before it starts moving back the other way. Likewise, if you throw something up in the air before it can start coming down, it has to instantaneously be stationary before it starts falling again. So we let v equal 0, 2 minus 2t equals 0, and therefore t is equal to 1. So that's the when it changes direction. And what about where? Well, we want to know where is the object after 1 second. So what's that? 1 plus 2 times 1 minus 1 squared. That's going to be 2. So that's when and where it changes direction. Find the distance traveled in the first 4 seconds. Okay, so the point here is that for the first second, it is traveling in one particular direction and it ends up at 2 meters, so we know it's traveling sort of from O to 2 meters to the right of O, or 2 meters in the positive direction. But then at that moment it stops and it starts going back the other way. So if we're going to find the total distance that it travels during the first 4 seconds, we need to split this up into 2 parts. Now I do know that it's going in a positive direction for the first second and then in a negative direction, so I do know that the first part's going to be positive. But if I wasn't sure of that, I could just take absolute value of everything. So I could say, well, this is the distance that it travels in the first second, so that's the change between its position at time 0 and time 1. And onto that I want to add the change in its position between time 1 and time 4 seconds. So just be clear on what that is. That's the distance it travels in the first second, or the displacement in the first second, and the displacement between second 1 and second 4, which is when it's moving in the other direction. So I want to calculate those separately. So I already know that it's, I already worked out that just above, that at time 1 it's at 2, its displacement is 2, so that would be 2 minus 1, and then this one here at time 4, so we worked out at time 4 that it was, what, 9, that's minus 7 I think, wasn't it, at time 4, minus 2, so altogether that's going to be 1 plus 9. So altogether it moves 10 meters in the first 4 seconds, but only 2 of those meters are sort of in the positive direction, aren't they? Or we should say 1 of those meters, because actually at time 0 it's already at a position of positive 1, isn't it? So it moves 1 meter sort of to the right and then 9 meters back in the other direction for a total distance of 10. Alright, and finally, part G, find the particle's average speed. Well, for average speed, we're going to use distance over time rather than displacement over time. And that's going to be 10 over 4, so that's going to be just 2.5 meters per second. Now, we didn't have to do a lot of calculus in that one. There's only a tiny bit there where we differentiated, but in some of the questions we'll have to do a lot more calculus. But this one was more, I guess, to try and highlight some of the conceptual stuff, particularly about changing direction when we're considering straight line motion.